Okay, for this question here, we're looking at the construct the understanding, matching the graph with the correct equation. This has a lot to do with the math lab that you worked with yesterday, specifically that chart that you worked with, where you talked about valleys and hills. I'm going to talk a little bit about that now. So without a graphing calculator, we have 4 graphs to pick from. Notice, I'm going to show you something here. If we talk about a parabola y equals x squared. Now, we all know that that's a valley such as that. Notice that if we have y equals x squared, the exponent is 2, but there is only one critical point. There's only one minimum or maximum, in this case being a minimum. So I'm just going to include this with our work here. So I'm going to put that picture right here, and I'm going to label that critical point right here. And I'm just going to point out that that is y equals x squared, and that there's one critical point. One critical point. A critical point is where a maximum or minimum occurs. Okay? Now, that being said, exponent of 2, one critical point. Let's look at the cubic function over here. This graph is a cubic function. A couple of characteristics. If it's a cubic function, it must have 1, 2 critical points. Notice the number of critical points is 1 less than the exponent. Okay, so this f of x function matches with that equation. Now, if we want to double check that, we can graph that on our calculator. That also being said, that notice the coefficient in front of x cubed is positive. This is 1x cubed at the beginning. If it's 1x cubed, the graph must fall to the left, which it does. Notice how it falls over here to the left. I'll put an arrow here. And then it rises to the right. Rises to the right. If this was a negative 1x cubed, it would have been reversed. It would have risen to the left and fallen to the right. Keeping with that same characteristic, that the number of valleys and hills, the number of critical points is a 1 less than the exponent number. Notice this graph here of g of x. It has 1, 2, 3 critical points. 3 critical points, 1 valley and 2 hills. So that tells me 3 critical points that is a power of 4. Something with a power of 4. Now notice we have 2 to pick from. We have this function and this function. Well, because it opens down, the graph continues down, it opens down, that's going to be this equation with the negative coefficient of x to the 4. Okay, so this graph will match that function. It's a quartic function, so it has 3 critical points. And since x to the 4 is negative, it opens down. We'll go down to this one. This one I call a tooth function. It kind of looks like a tooth that's upside down. It also has 3 critical points, 2 valleys and 1 hill. So that power of 3 means that this is an exponent of 4. And since it opens up, it has to be this one. Okay? And the last one has 1, 2, 3, 4 critical points that I'm labeling. 2 valleys and 2 hills. 4 critical points means a power of 5. It's a power of 5, so that would match perfect with that equation. That is also called a quintic equation. And since it has 2 hills and 2 valleys, it's a quintic equation that would represent that. Last thing that I forgot to say is for all of these functions, if you substitute a value of 0 for x, remember if you let x equal 0, you're going to get what we call the y-axis intercept. I'm writing this down in the lower corner here. The y-axis intercept. And notice for all of these polynomial functions, if you put a 0 in for x, what will the y-axis intercept be for all of them? Take a quick look at that. Proto, pay attention. Bisignano, stop talking. Okay. What's the y-axis intercept? Lobo. Lobo, pay attention. Oh, okay. Notice it is 4 for all of them. Okay, you can proceed to the next problem.